Hi, I'm Vibhu, and today I'm going to be talking about IMDb. No, not the IMDb you're probably thinking of. The in-memory database, another emerging database in the recent years. So let's take a quick look on the outline of the topics that I'm going to be discussing today. I'm going to be talking about what IMDb actually is and why do we use it. How do we implement it and its various uses. So let's get into it. An in-memory database or IMDb stores computer data in a computer's main memory instead of a disk drive to produce quicker response times. As we know that accessing data from the main memory is much quicker than an external drive. Accessing data stored in memory eliminates the time needed to query data from a disk. Industries that benefit from in-memory databases include telecommunication, banking, traveling, and gaming. An in-memory database is also referred to as a main memory database, MMDB, real-time database, RTDB, or in-memory database system, IMDS. So what is an in-memory database? An in-memory database keeps all its data in the random access memory of a computer. But there is a significant downside to an IMDb. That is the volatility of RAM. So what does that mean? It means that if your computer crashes or shuts down abruptly, all your databases that you were currently working on will be erased and you can't recover them. So the solution to this is the development of non-volatile random access memory, which maintains data after a crash or a power loss. Flash is one example, but a major drawback is the limit to how many times flash memory can be erased and rewritten. Now let's take a look at how IMDb is different from simply storing data in shared memory segments. In-memory databases maintain components of the ACID attributes of data storage engines. The ACID properties include atomicity, consistency, isolation, and durability. While in-memory databases may relax the durability property based on non-persistent storage, they commonly support the other properties such as atomicity, consistency, and isolation. Moving on to the differences between on-disk databases and in-memory databases. As we know that in the case of on-disk databases, all the data is stored on the disk and the disk input-output is needed to transfer the data. Whereas in the case of in-memory databases, all the data is stored in the main memory. So no need to perform disk input-output to query or update data. In case of on-disk databases, the data is always persisted to the disk. This means that the data cannot be lost in case of an accident. Whereas in IMDb, data is persistent or volatile, depending on the IMDb product. For on-disk databases, traditional data structures like binary trees are used, whereas specialized data structures and index structures are used in IMDb. On-disk databases support a very broad set of workloads, for example, OLTP, data warehousing, mixed workloads, etc. Whereas IMDb is used for high performance optimization. So now the question arises, why use an IMDb? Applications that manage vast quantities of data and require rapid response times can benefit from IMDb architecture. The data analytics industry increasingly relies on IMDb systems. The benefits of an IMDb include faster transactions, no translation, and multi-user concurrency. So let's take a look at the advantages and disadvantages of IMDb. The advantages of IMDb are that it is faster than traditional databases. There is no need to deal with secondary memory, which saves a lot of time during memory access. Since the requirement of accessing the slower secondary storage is eliminated, we can now perform several algorithms with IMDb which would not be feasible for disk-based databases. Coming on to the disadvantages, we already know that a typical IMDb is not persistent. So when an application closes by accident, all the data stored in an IMDb will be lost. So those applications which require a higher degree of data persistence, may not be suitable for using an IMDb. An IMDb stores all the data in the main memory, which might limit the amount of data that can be stored. Generally, it is much lesser than the amount of data that can be stored in a disk-based system. So how to cope with these disadvantages? An application developer needs to understand that data loss is a possibility when working with an in-memory database. There are several approaches such as persistence and replication used to mitigate data loss scenarios, but data loss is still a possibility. If a database is opened using the persistent in-memory mode, changed content will automatically be written to secondary storage when the database is closed. In addition, the developer can persist change to secondary storage on demand. Replication. Many database systems support replicating changes to another database instance. Using replication allows data that may have been lost from the in-memory copy to be recovered from the replicated copy. So how does an IMDb actually work? Data storage in an IMDb relies on a computer's random access memory or main memory instead of traditional disk drives. Data is loaded into an IMDb in a compressed and non-relational form. The data is in a directly usable format without the barrier of compression or encryption. It allows for indirect navigation from index to row or column and is a read-only system. The speed of an IMDb is made possible by lack of translation and caching. The data is used in the same form as the application that contains it. Data access is managed by an IMDb system. An IMDb system can also act as an read-only analytic database that stores historical data on metrics for business intelligence applications. This eliminates data indexing, which can reduce IT costs. Multiple core servers, 64-bit computing, and lower RAM prices have made in-memory analytics more common. So the next question that arises in our mind is that how is data accessed and changed in an in-memory database management system? Data in an in-memory database is ready to go, where data in a disk block may be compressed, encrypted, flattened, or encoded. Data in memory is in a directly usable format. It also has structure that is independent of disk blocking issues, allowing direct navigation from column to column, row to row, or index to row, allowing changes to be implemented by allocating memory blocks and rearranging pointers. Now, how is in-memory data shared among multiple tasks? The answer to it is twofold: faster and faster. For those familiar with the transactional file server (TFS), which can be used to share a database among user processes in the same computer, in the office LAN, or across the world, the database can be managed in memory by the TFS. This is faster than on-disk databases managed by the TFS. But the faster way to share one database among multitasks is to run a single process with multiple threads, where each task is running in its own thread. This form of an application runs on one computer and allows each thread to access the database directly in local heap storage. It also circumvents the need to read unchanged database objects into a local cache, because the original data can be viewed directly from the database memory. This is a very fast way to share a database in a multi-user mode. Another challenging question arises that are all the embedded databases also in-memory databases? So first we need to look at what are embedded databases. An embedded database can be defined as a database engine that runs within an application and does not require other processes to be installed, configured, or accessed. The storage media for the data managed by the engine is implementation dependent. Originally, most database engines used a hard disk for data storage, as the amount of memory available would not allow for sufficient data volume for useful data sets. As the size of memory increase, many vendor big, as the size of as the size of memory increase, many vendors began adding in-memory capabilities. Today, many database engines, embedded or traditional, have some support for in-memory. Today, many database engines, embedded or traditional, have some support for in-memory. So the most important part is how to implement an in-memory database. To avoid the risk of losing data in a power outage or a computer crash, non-volatile random access memory should be used. Flash is commonly used despite its high cost and limitation in number of times memory can be rewritten. This can help in-memory databases maintain data after a power loss or crash. Reading a database from flash is faster than using a disk drive. That is why NVRAM chips are being developed that provide a more persistent memory than flash. So now let's take a look at the several uses of IMDb. In-memory databases are commonly used for real-time banking, retail, advertising, medical device analytics, machine learning, and billing subscriber applications. Online interactive gaming, geospatial GIS processing, processing of streaming sensor data, developing embedded software systems, application in transport systems, network switches and routers, applications in transport systems, network switches and routers, fulfilling the requirement of e-commerce applications. The list of softwares that use IMDb are Aerospike database, which uses flash optimized in-memory open source NoSQL database. Second, Altibase hybrid database that combines an in-memory database with a conventional disk resident database in a single unified engine. Third, Apache Ignite. Apache Ignite is an in-memory computing platform that is durable, strongly consistent, and highly available with powerful SQL, key value, and processing APIs. Fourth, OrangoDB, written in C++ and optimized for in-memory computing. In addition, OrangoDB integrated RockDB for persistent storage. In addition, OrangoDB integrates RockDB for persistent storage. And there are many more softwares that use in-memory databases. In conclusion, in-memory databases do use disk for data change operations, but they use it in the fastest possible way. And IMDb can be useful for some users while can be useless for the others. It all depends on the application requirements. So that's it from my side, and thanks for paying attention.